All right, so let's see how this goes then. Here's something new, something I haven't tried before. We'll see whether this works or not. For starters, I've put up a question in Feedback Fruits just to see if we can get this all working. So the code to Feedback Fruits is still available to you. You can see it on the stream. But let me know whether you can hear me, whether you can see me. Should all work. While we do, allow me to talk a little bit about chat, because I see that my TAs are already having to click quite a lot. So the idea for chat is that we try and use it as a means for you to ask me some questions. I see that other things are also popping up in there. Perhaps also unrelated questions to the course. I hope that I can trust on some level of your professionality to make sure that we can actually use chat in that way. Now, to answer some other questions that I got quite a lot already, again, while we get this set up and while people join our Feedback Fruit session, yes, I will be uploading the voice of, or the recording of this on YouTube, likely an edited version in which, for example, I will cut this bit out. I assume the stream will invariably break at some point. Audio might quit. The video, which is just my phone, which I've tried to use as a webcam, might stop. All kinds of nice things might happen. So stuff like that I'll cut out, and then the result of that I'll upload on YouTube. Now then, let's see. 112 people in Feedback Fruits. That seems about right so far. I see your question about the final exam. No, I cannot say anything about that at the moment. The current regulations are until the 31st of March, and if I remember correctly, our exam is after that. So we'll have to see what happens with that. Okay, now let's see if I can make all of this work. So let's do something like this maybe. Just setting up some small things here. Let's see. Yeah, that seems to be working all right. Then I also prepared today's slides here. So let's see how we go about doing that. Maybe something like this. And let's see if we can get started. So, as you are used to by now, we of course start the lecture with some questions about last week's homework. So let's try and get started with that today as well. We might not be in a lecture room, but we still appreciate some quick feedback on how the homework for the course is going. think that's all we're gonna get, so let's take a quick look. Okay, makes sense, I suppose, although perhaps this morning during our online lab some work could have already been done. Now let's take a look at assignment 4. So how long did you spend on that? Okay, that should be good. Let's take another quick look. Nice spread of answers, but it seems that overall about 2 hours. Okay, and I think we have one more. Yes, so you should have watched some videos for today, as well as read some chapters of the book. Let's see how long it took you to prepare. So to repeat this once more, if you missed our introduction, yes, I'm aware I can disable chat, but I hope that we can use chat for you to ask me some questions in addition to feedback fruit. If it doesn't work at all, then I guess we'd have to disable it, but I'm hoping I can count on your cooperation in making this work. And TAs are on top of things as well. I hope that that helps. So let's give you another 10 seconds to answer this question. And let's take a look. All right, and that's going to be a challenging setting today. With no preparation at all, I can imagine many of the questions that I will be asking you will be perhaps too hard to answer, but we'll see how that goes. Now, of course, you had a midterm exam yesterday, the last opportunity we had to get you all together. We made the most of it. So we have 2 quick questions about that as well. First of all, level of difficulty, and the next question will be about duration. Again, some quick feedback while people might still be joining the stream, and then we'll really get started. Okay, 10 more seconds to give me an answer if you have one. Yes, Lich. Indeed, the time in Osiris was 1.5 hours. I tried contacting him about it, but Osiris is not something I have direct control over. So unfortunately, this could not be changed in time. My timetable did show a time of 2 hours. And if I remember correctly, it's also on the exam. So perhaps that could have helped too. Okay, let's take a look. All right, that's a nice distribution. I can be pretty pleased with that, I think. Last question is about the length of the exam. So did you have enough time? Based on the number of people that left early, I think I know where you're going with the answers here, but let's see anyway. That's not the button I meant to hit. Let's see. Okay, there we go. 5 more seconds to give me an answer if you have one. Correct, Paul. You can see them on feedback fruits, but as soon as I close the question here, which I will be doing now, you can see the answers on stream, right? So you should now be able to see them here. Okay, that's a fair distribution. Thanks for all your feedback. With that, let's jump in on to some real questions. So today we will be talking about enumerators, as well as the notion of encoding inputs, though we won't spend a lot of time talking about that, as well as decidability. Now, before we talk about enumerators, however, you've also watched a video, hopefully, on something called the Church-Turing thesis, which is quite an important thing in this course. So let's see if you know what that is all about first. So here we go. Which of these statements about the Church-Turing thesis is true? Let me also open it up in feedback fruits. There we go. I'll give you a minute or so to give me an answer. All right, 10 more seconds to give me an answer if you have one. Okay, and let's take a look. Pavan, I'll try to do that to the best of my abilities, but usually I just wait for a right number of people to have answered, so we'll see. Okay, let's take a look. Nice distribution of answers. Now, as the question already indicated, right, multiple options are correct here. So let's see if we can figure out which ones. Now, in a lecture setting, I would probably ask you, okay, answer A, who can tell me why this is incorrect? But I guess today I will have to do most of the talking. So let's see if we can make that work. So answer A, if we didn't have it, we would have to face the limited capabilities of lambda calculus. Well, I would argue that the thesis indeed shows, as someone already pointed out in chat as well, that lambda calculus and Turing machines are equivalent in terms of their capabilities. But this is not, or rather the fact that we would have to face the limited capabilities of lambda calculus isn't really an issue. As I said, both are equally expressive. So indeed, this wouldn't be a problem. Now, Arcade Official, I like your suggestion, but currently I think Twitch chat is still, let's say, too immature to handle this. Hopefully that gets better somewhat later in the lecture. For now, we'll make do. So answer B is an answer that is correct, right? So this thesis shows there is no point trying to find algorithms for problems of which we can prove the impossibility of solving them. So what the thesis states is that any model of computation we can currently think of can be modeled or simulated using Turing machines. So these are all equivalent. This is also why answer E is correct. That means that answer B is also correct, because if we can show that a Turing machine cannot solve a certain problem, then through this thesis we can show that no machine or algorithm or whatever you want to call it can solve the problem. So indeed, this thesis is a good reason as to, well, stop trying or to not look for algorithms or solutions to problems that we can prove have no solution for a Turing machine. So answer C, this thesis ensures that we can prove the impossibility of solving certain problems, very vaguely formulated. We'll look into this a little bit more next week when we talk about undecidability, and we will see problems like the halting problem and the word acceptance problems for Turing machines that are problems that we can prove have no solution. So they are problems that are indeed impossible to solve. Answer D, without it we cannot build computers. Well, of course we could always build them. The problem is that without this thesis we wouldn't know, let's say, the power of these machines, right? So to what extent are these computers able to solve certain problems or not? So answer D, sure, we could build them. It's just that we don't really know what they can and cannot do. Okay, answer E, I think I discussed. Like I said, the thesis shows or claims that all machine models are equivalent, all machine models that we know for now. So Turing machines, non-deterministic Turing machines, lambda calculus, one tape, infinite tapes, a small alphabet, a larger alphabet. And therefore, indeed, using this thesis, it's true that we do not have to worry about the power of the model we use. So we can focus on the Turing machine and by extension reason about other machines as well. All right, let me quickly check whether there have been any questions asked that I can do something with. Is the Church-Turing thesis related to answer C? Yes, I would argue it is to some extent. So I agree with you, Pavon, that Hilbert and Gödel play an important role in material from this course as well. Unfortunately, not in material we discuss all that much. So Gödel's incompleteness theorem, for example, is something we touch upon a little bit. But for answer C, right, the impossibility of solving certain problems, we will see next week when we talk about undecidability, that there are indeed problems that we can prove have no solution for a Turing machine, and using this thesis, or cannot be solved using a Turing machine, and using this thesis we can somewhat by extension show that we cannot solve them using any of our models of computation. All right. I think that was a nice question to get us started. let's delve into some questions about enumerators. And let's see how that goes. So like I said, today we have 3 topics to discuss: enumerators, encoding problems, as well as decidable languages or decidability. Encoding problems we'll spend a little bit less time on because it's something that, although relevant, is not all that useful for the other material we'll discuss in the course. It's a bit of a sidetrack, if you will, but let's start with enumerators all the same. So, first question for you. Let's see what you remember about PDAs. They didn't feature heavily in our midterm, but perhaps you, or hopefully you, studied them regardless. So, does a language exist for which no PDA exists, but for which an enumerator can be constructed? It's a yes/no question. Feedback Fruits is happy to hear your answer now, and I'll give you half a minute to a minute to think of the answer and give it to me. All right, 5 seconds left to give me an answer if you have one. And let's take a look. Okay, 80% for answer A, yes. All right, now again, normally I'd ask you, can someone tell me how? But for today, it's going to be me talking a little bit more, at least for the start. So very briefly, a recap of what an enumerator is. An enumerator is a special type of Turing machine that, instead of taking a word and determining whether it's in a language or not, it doesn't take any input, it just starts printing words. So every enumerator has a certain language, and what it will do is it will start printing all of the words in that language. Now, take as an example the language given here. So a to the power n, b to the power n plus 1, c to the power n plus 2. This is a language that we cannot construct a PDA for. So we cannot construct a PDA here because there's 3 counters we need to keep track of. And remember, these PDAs, these push-down automatas, they work with our context-free grammars. And in our context-free grammars, we could, for example, build a to the power n, b to the power n. But constructing a grammar for something like this, or context-free grammar for something like this, I should say, isn't going to work out. Now, we haven't seen a formal proof method for that. There is a pumping lemma for context-free languages. But we only study the pumping lemma for regular languages. But for this language, it is indeed impossible to build a PDA. However, building an enumerator shouldn't be a problem. After all, what can we do? Well, we start with n is 1 and we print the word, right? So we print A, B, B, C, C, C. And then for n is 2, we print the word AA, B, 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 C, 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 and so on and so forth. So indeed, it's not something that we can do using a PDA because of these free counters we need to keep track of. However, it is something we can do for with a Turing machine, and we can simply enumerate all of the strings in this language. Now I see chat is starting to quiet down a little bit. Let me see if there's any questions I can answer about this, or no, you seem to have answered most of them yourselves already. Thank you for that. All right, then let's move on to the next question. I see a good question being put in there now. Let me see if I can quickly answer it. So Hyper, you're asking about, can we disprove that a language is recognized by a PDA with the pumping lemma? Yes, we can, but a different form of the pumping lemma. So in the course, we only study the pumping lemma for regular languages. There is also a pumping lemma for context-free languages, but we don't study it in this course, so you don't have to know about it. Okay. I see another question about Turing recognizability and enumerators and their relations. That's great, because one of my future questions is going to be about that. But before we do, let's take a look at one of these enumerators in action. So let's say that we have a language that is Turing recognizable, and we have a machine that recognizes the language, right? If it's Turing recognizable, this machine M must exist. Now then, I'm trying to create an enumerator for our language using this recognizer. And I wonder whether the machine I'm giving you here is indeed an enumerator of L. I'll give you, again, a minute or so to answer the question. All right, another 10 seconds left to give me an answer if you have one. And let's take a look. Ooh, that's a very nice split. All right, 51% for yes and 49% for no. Excellent. Seems like this is a good question to ask. So, L is a Turing recognizable language. M is a recognizer of L. What does that mean? Well, a recognizer means that if we put a word into it, and the word is in the language, then the machine will accept the word. However, if a word is not in the language, then our machine may reject the word, which you might expect, or it could loop on the word. This is why it's a recognizer. If it were a decider, it would always accept or reject, no matter what word we put in. However, a recognizer could loop on words that are not in the language. And that's exactly the problem with the enumerator we're trying to build here. So in step 2, it's possible that when we run our machine on word si, that our machine loops. The word si could not be in the language, and therefore our machine could loop, and we would never continue with the next word. So consider an example where the first word is in the language, the second word is not, and the third word is. Then the first word will be printed, right? We will run the machine on our first word, the machine will accept, and we will print it. However, when we run the machine on the second word, then the machine could loop because the word is not in the language. So we would never get to run the machine on word number 3. Now I get a good question here. Why would you use a recognizer if it could loop on words that are not in L? Well, as we will see, and as you hopefully have already seen, there are some languages that are Turing recognizable, but are not decidable. So we have certain languages that we can recognize, right? So words that are in it, we will accept, but we cannot decide. So words that are not in it could loop. Does that mean that an enumerator must halt? No. So an enumerator can also enumerate an infinitely large language, in which case the enumerator will never halt, because for an infinite language there's always words to more words to give. So an enumerator could run forever, and it should print all the words in the language at some point in some order. It could even have duplicates, that's all fine. But a recognizer for words in the language should halt and accept, and for words not in the language can either halt and reject or loop. Then final question I'm going to answer about this one before we move on. So Frostbite asks, why would dovetailing solve this problem? Right, so what would dovetailing for this look like? Well, what we would do is first, we would run it for one step on word 1, for example. Then we would run it for one step on word 2, and for one step on word 3, and so on and so forth. Which means that surely at some point, a word that is in the language would indeed be accepted and printed, right? Every word that's in the language must be, will at some point get its steps. So you could make some sort of one of these diagrams that you may have seen, right? So first run it for one step on word 1, then run it for 2 steps on word 1 and 1 step on word 2. Then for 3 steps on word 1 and for 2 steps on word 2 and for 1 step on word 3, something like this. So in this way we can dovetail it indeed, as you said, and we can make sure that every word that the machine would halt on at some point is fully processed by the machine and is printed by the enumerator. Okay. I also see a question about enumerators and deciders. Now let me take a quick look, because I think that is the next question we will be talking about. Well, it's at least similar. So let's take a look at the next question. If a language L is decidable, does an enumerator exist for this language that enumerates the words in lexicographic order? So lexicographic order means dictionary order, right? So A would come before AB, and AB would come before DC, for example. So if a language is decidable, does an enumerator exist for this language that enumerates the words in lexicographic order? Feedback Fruits is happy to accept your answer, and I'll give you about a minute or so to give me one. right, 10 seconds left to give me an answer if you have one. I just realized I forgot to mute while typing. Sorry for that. I can only imagine it must have been quite loud. Okay, let's see what you think on this one. All right, an overwhelming majority for answer A, which is yes or true or whatever you want to call it. Well, you're quite right. So how does this work? Well, if a language is decidable, then there's two options. Either it is finite or it's infinite. Okay, that's not true for decidable languages, that's true for languages in general. But let's consider these two options anyway. So if the language is finite, then surely we can list all of them and therefore enumerate all of them. Right? For a finite language, worst case, we would write them all down and our Turing machine would just be encoded to print one of these after another. Then, what about if the language is infinite? Well, in that case, you might think it's a little bit more problematic, right? Because how do we determine for an infinite language which words to list? Well, what we can do is we can simply start listing all the possible words in sigma star in lexicographical order. So we start with A, and then AA, whatever is the next one. And what we do is we feed this word into a decider, so into a machine that decides L. Since L is decidable, such a machine must exist. Now this machine is a decider, so it will either accept or reject. And if the machine accepts, then we should print the word, because the word's in the language, so we should enumerate it. And if the machine rejects, we should skip the word and move on to the next one. So again, we could simply list all the words from sigma star in lexicographical order, and one by one feed them into our decider, which then determines whether we need to print it or not. All right. Let's see. I hope that answered the question that was asked as well. So no, our enumerator does not have to go over every word. Instead, we know all the words in sigma star. We can put them in lexicographical order. Yes, there are infinitely many, but we can just do them one at a time. And because our machine is a decider, we cannot, it cannot loop. It must always accept or reject. Okay. Let's take a look at the next one. So let's do this one and then let's have a short break. I mean, these are still lectures after all. How might we show that a language L is decidable if and only if there is an enumerator that enumerates the language in alphabetical order? So we have an if and only if statement here, right? So remember, whatever we pick, we need to show something in two ways. Feedback Fruits is happy to hear your answer again. I'll give you 1 or 2 minutes and then we'll take a look. right, 10 more seconds to give me an answer if you have one. And let's take a look. Okay, a quarter of you for answer A, about half of you for answer C, and all close to a quarter for answer D again. I say again, I don't know why I did. Don't think we've had an answer D yet. Let's take a quick look. So answer A, by constructing the decider and the enumerator for L and proving that the two are equivalent. Now, that idea might sound good, but the question is, how do we construct such a decider, right? So this answer is nice, but I would argue that in the form that it's here is still a bit incomplete. So we need a little bit more, but perhaps it's a way to get started. Answer B, well, a few people picked it, so let's quickly address it. By giving a language A that has both a decider and an enumerator that enumerates the words in A in alphabetical order. This is not sufficiently general proof. Our statement, although not explicit, is about all languages, right? So all languages are decidable if and only if there is an enumerator that enumerates the language. So giving just one example isn't enough to show such a for all statement. Then suppose L has a decider D, so we're looking at answer C now. Suppose L has a decider D and an enumerator N. Now feed each word that N prints to D and accept only if all words are accepted by D. Okay, quite a lot to parse here. So suppose L has a decider as well as an enumerator. Okay, then feed each word that N prints, okay, that our enumerator prints, feed it to D and accept only if all words are accepted. Well, this doesn't really tell us anything about the order, right? So we wonder if there is an enumerator that enumerates the language in alphabetical order. And our answer doesn't really say anything about that. Furthermore, we want to prove an if and only if here, and this answer is only hinting at one of the implications, not the by implication. Okay. That leaves us with answer D. None of the above are correct. Well, like I said, A might be, but is at least in its current form not sufficiently complete. So what I suggest we do, let's see, are there any more questions I should answer now? I don't think so. I see one of our TAs has already answered one or two of them. Thank you very much for that. Okay. Then what I suggest we do is we have a small break. After all, it's 2:30. And in about 15 minutes, I'll be back and we will discuss the proper way of doing this. So we'll look at the same question, but I'll give you two other alternatives for you to take a look at. And we'll see how we can make this work. See you in 15 minutes. All right, welcome back. Let's see if we can get this started again. So if you're just joining us, this is the lecture for Automata, Computability and Complexity Theory. Twitch chat is a place you can use to ask me some questions if you have some. Please use it only for that purpose. Me and the TAs are heavily monitoring it. But hopefully before the break, I think just before the break especially, it was going quite well. Let's hope we can keep that going. Now then, before the break, we talked a little bit about this statement. How might we show that a language is decidable if and only if there is an enumerator that enumerates the language in alphabetical order? We saw that the options currently on the slide all didn't really work. So let's take a look at two other options. Here we go. As you can see, these are a little bit more extensive. So I'm not going to read them out in full. I'm just going to give you a bit of time to read them and to then give your answer in feedback fruits. All right, 10 seconds left to give me an answer if you have one. And let's see what you've made of this. So, just over half of you for answer A, about a quarter for answer B, and about 20% still believing that none of these will work. All right, let's take a look at answer A then. So answer A states that suppose L has a decider. Okay, so this is going to show the if-then statement the first way, right? It's going to say if L is decidable, then there is an enumerator. Now, as we've seen, if we have a decider, we can make an enumerator in pretty much whatever order we like, right? We can just enumerate sigma star, feed all of the words into our decider, and our decider will tell us whether it should be printed or not. So surely we can then also enumerate sigma star in alphabetical order and print those that the decider accepts. So far so good. Now conversely, okay, so that's the statement. If there is an enumerator that enumerates the language in alphabetical order, then L is decidable. Well, let's take a look at that. So if we have an enumerator that enumerates it in alphabetical order, and we are given a word, and we need to determine, is this word in the language, yes or no? What could we do? Well, what we could do is we could simply run our enumerator, and at some point, either our word will be printed by the enumerator, meaning that our machine should accept, or a word will be printed that in alphabetical order comes after the word we are looking for. And as soon as such a word is printed, a word that is later in alphabetical order than the word we are interested in, we know that the enumerator will never print our word, because the enumerator enumerates them in alphabetical order. So our decider can indeed be made using this enumerator. Now, you might think, okay, but what if there is no word after the word we're interested in, right? For example, if L is the empty language, as Ellenson points out, or what if we happen to be looking at the last word in alphabetical order? Well, even then, we can make this work because our enumerator would halt, right? So if this is some finite language, like the empty language is, it will at some point halt after printing all of them. If the language is infinite, it will continue printing strings forever, and we can wait for the next one, or for one that is later in alphabetical order. So answer A indeed works. Well, that immediately eliminates option C. So let's take a quick look at answer B. Suppose L has an enumerator. Now the decider can be constructed by adding a chain of states to recognize the word to the decider for each word that is printed. So essentially what we're doing is we're adding a chain of states for every single word. Now that may sound like a good idea, but the problem is that for an infinite language, we would have infinite words and therefore infinite states. And remember, a Turing machine can do a lot. It can handle an infinite tape, but it requires to have a finite number of states. So we cannot construct a decider in this way, because if we add a chain of states to recognize each and every word for infinite number of words, we would be adding an infinite number of states, and that's not allowed in our Turing machine model. Okay, let's see if there's any questions left unanswered before we move on to the next one. Yeah, so Jonathan, I would say an enumerator halts when either it has printed, no, not either, when it has printed all the words in the language. Right, so it will only ever halt for finite languages. And for infinite languages, it will continue running forever and continue printing words forever. Okay. I see no other questions, so let's hope that means it's safe to move on. Let's see. Yes. Let's take a quick look at time. Yeah, let's make this the last question we do about enumerators. So an infinite language can be enumerated using an enumerator. We've already talked about this a little bit. How can we make sure that works? Because as I just mentioned, Turing machines are not allowed to have an infinite number of states, right? The number of states must always be finite. How can we still make that work? Feedback Fruits is open for you to answer this question. I'll give you a minute or so, but likely a bit more, to give me an answer. Okay, 10 seconds left to give me an answer if you have one. All right, let's take a look. Okay, nice division of answers again, but B is the most popular. So let's quickly take a look. So answer A says this is possible because there's always some kind of pattern in the language. Seems to be a bit vague still. Let's set it aside for now and take a look at answer B first. Yeah, this looks like a better order of going about things. So this is possible by using a version of the pumping lemma with an arbitrary number of parts of the division. Each recognizable word consists of a finite number of pumpable parts. This seems to be some sort of, let's say, overgeneralization of generalization of the pumping lemma. So we've discussed it for regular languages. As I mentioned before the break, there is a version for context-free languages that we do not study in this course. And you might think, okay, but maybe there's also one for recognizable languages, right? Well, unfortunately, there is not. So this is not the right answer. However, answer A is the right answer. So indeed, there must be some certain pattern to these languages. And how do I know that? Well, I know that because of another theorem that we've seen. We've seen a theorem, or at least you should have seen it when preparing for today's class, that any language that is Turing recognizable can be enumerated. Now, if a language is Turing recognizable, what does that mean? It means there is a Turing machine that, given a word in the language, will accept the word. Meaning there is some machine with a finite number of states that can recognize the word, right? It can accept the words that are in that language. And on that same principle, we can build our enumerator. So any of these words can be accepted by a Turing machine with a finite number of states, and therefore our enumerator must also be able to enumerate them using a finite number of states. Now, answer C was fortunately picked almost not at all, which is great, because indeed enumerators are a very nice theoretical idea, but are also very practical, as we can use enumerators to show languages to be Turing recognizable. Now, whether you think of Turing recognizability as being a practical application or not, that's perhaps another question altogether. But yeah, we can use enumerators for this purpose. Answer D, this is impossible. Infinite languages might not be recognizable and therefore do not always have an enumerator. Correct. An infinite language may indeed not be recognizable. But those that can be enumerated can indeed be enumerated by an enumerator with a finite number of states. So the ones that are recognizable can be enumerated with a finite number of states. So Paul, to answer your question, language that is enumerable is also Turing recognizable. So this is one of the theorems that Sipser discusses. A language is Turing recognizable if and only if it is enumerable. And they give a nice proof for that as well, I think. How you can construct an enumerator knowing that it is recognizable and the other way around. Okay, let's see if I missed anything else. Haku, you have a nice question. The question doesn't specify that the language is recognizable. Does this question imply all infinite languages can be enumerated? Let me see. An infinite language can be enumerated using an enumerator. How is this possible? Yeah, okay. So I agree the phrasing of the question is not great. Could use some improvement perhaps for next year. But there are infinite languages that are recognizable, and these we can then also enumerate. Perhaps that's what the question phrasing should be instead. Okay, I see no other questions at the moment. I do see some other helpful links being shared, which is great. So someone is linking a page of Sipser, someone's linking a nice Stack Exchange question. Good. Let's see. Yes, so let's talk a little bit about this. Are there any questions? I checked earlier. So someone asked, will the course ever touch upon the RAM model? Earlier, I think before the break already, a little bit. So we will talk about this a little bit when we talk about the complexity theory part. I will then explain why, even for the complexity theory part, we can focus on Turing machines. And I will do that by showing or explaining how we can show that the RAM model and the Turing machine model are still equivalent in terms of what they can do. And I will talk a little bit then about the overhead required in terms of time complexity specifically when transforming something from the RAM model to the Turing machine model. So yes, we will talk about it a bit, but not very in depth. I will mostly talk about it in terms of showing you why we don't have to talk about it, if that makes sense. Then, what definition of lexicographical order does the course refer to? There are several unequal definitions. Yes, this is a big mess. I was answering some questions during the break as well, looked up some stuff. One of our TAs fortunately found a nice wiki page about this. Perhaps he can also share that in chat in a moment. There's also one in the book, and we will stick to the one from the book as much as possible. Even though the book is arguably also a pretty strange definition. So lexicographical order is what you would call dictionary order. Only the book says that shorter words come before longer words. So, for example, whereas A would come before, let me give a good example here. Whereas AA would come before B in a dictionary, in the lexicographical order that we use because the book uses it, B would still come before AA simply because B is shorter than AA. And yes, I see the link has been posted in chat. Thank you for that, Philippos. All right, I see one more question popped up, but I'll do it next time we get to these. For now, let's dive into the next little bit, which is about encoding problems. Now, as I mentioned before, encoding problems is a topic that is a part of this course, right? It's part of showing how we can model problems that you may already be familiar with, for example, from algorithms and data structures or algorithm design, how we can model these in such a way that our Turing machines can still operate on them. So it's an important topic in that sense. Then again, we aren't teaching you, or we have no intention of teaching you how to implement Dijkstra's algorithm or Ford-Fulkerson's algorithm on a Turing machine. That would be horrible. I don't think anyone in their right mind should try to do that. So we'll only do one or two questions about this, one or two questions that I particularly like to do, and then we'll move on to the last topic of today, decidable languages. So let's see, I didn't want to do this one, but I thought this one might be nice. So imagine that we have found some way to encode a graph so that a Turing machine can read it, right? So you may remember different ways of encoding graphs or representing graphs from algorithms and data structures. So we talked about adjacency matrices there, or edge lists or stuff like this. And this question is about that. So let me open it up in Feedback Fruits. I'll give you a bit of time to read it and give me an answer. All right, 10 more seconds to give me an answer if you have one. And let's take a look. Okay, F is the most popular answer with about 40% of the votes. Now, let's take a look at our problem first, right? So the problem is hopefully a problem that you recognize from algorithms and data structures. We have a graph, and the question is there a path between two given nodes? Now, hopefully you remember that this is something we can easily solve using something like a breadth-first search or depth-first search. So when instead of talking about Turing machines, we talk about our regular computers and we implement this in Python or in Java, we can just use a BFS or a DFS to find the right answer. Now the question is, can we encode the input in such a way that our Turing machine only needs to go through the whole thing once and can then return yes or no? Now answer A says yes, you need to ensure the edges in the description are in the right order. Okay, that's very nice. But my counter question would be, okay, but what's the right order? Knowing the right order means I know already the answer to the problem, right? I already know what the path is, and then I can put these edges exactly in the right order so that when I scan them once, I've indeed exactly found the path from some node S to some node T. So answer A, I guess technically it's correct as long as we know what the right order is. And since we have no way of knowing what the right order is without solving our problem first, I would therefore not consider this answer. Answer B, yes, this is trivial, always a very nice word to use, using an adjacency matrix. So what's trivial in this context? Well, it would mean that it's obvious. I would argue that that's definitely not the case. So an adjacency matrix, what would that mean? Well, we could, for example, first list all of the edges from node 1, and then all of the edges from node 2, all of the edges from node 3, and so on and so forth. Again, that's a good way to encode a graph, but it doesn't help us to do this in one single sweep. Why not? Well, consider a path that would go from node 1 to node 3, and then to node 2. Then I need to go back to find out what the edges of node 2 are, after I've discovered that from 3 I can go to 2, right? So I cannot do this in one path. Answer C, yes, it's a trivial using a list of edges as pairs of nodes. I would argue same issue here, right? If I need an edge that was listed earlier, then that doesn't work. No, since the problem is undecidable, well, we can solve it using BFS or DFS, so it's definitely not undecidable, it's definitely solvable. No, since there may be nodes without adjacent edges, okay, but as none of you picked this answer, I think we can skip it, but yeah, I don't see how this would formulate or how this would form a problem for our encoding. And the last one, no, since you cannot generally fix the order of the edges such that you do not need to look back. So this is the answer I would go for. Because like I said, it's very well possible that in doing our BFS, we now come across a node whose edge we have previously seen and we now need to consider. I think someone suggested, okay, but what if we repeat the edges a couple of times, right? So that, okay, we may have missed it, but don't worry, the edge will appear again at some point. So we can just continue reading and at some point we'll find it. It's a nice idea, but unfortunately that also doesn't really work. Because we should also in some way remember in what node of the graph we currently are, right? And remember our BFS or our DFS. In DFS we're only in one node at the same time, but we need to backtrack. In BFS we are in many nodes at the same time, and keeping track of this on a Turing machine would require writing that, right? What node are we at? We should write that. But then when we need to backtrack, we still need to move back on our tape to see, okay, what's the previous node we were at? So unfortunately, repeating the edges also wouldn't work. Okay. I think that covers these. Let's take a look at one more here before we close this topic. Like I said, it's not the most relevant topic for us to discuss. This was a very nice question about chess, which is amazing, but or chess, or I think it was chess, but great for people that are into chess. Feel free to check it out when we publish the slides later, but for the course, I think it's fine to skip it. There is one more I wanted to do here, which is this one. And the reason I want to do it is because this is a very nice problem from complexity theory that we may or may not end up discussing a little bit in the last week. So just as a quick exercise, see how well you remember your reasoning and logic. We have a language of true quantified Boolean formula. Now, a true quantified Boolean formula is a formula that starts with a bunch of these quantifiers. Remember reasoning and logic, for all there exists, for all there exists, all this kind of stuff. And now we have a formula here. There exists an x0 for all x1, yada yada, for which something is true. And the question is there a way to make this formula true? So is this thing true or not? Let me find it also in feedback fruit. It's encoding problem 6. So yes, this is a little bit of complexity theory, something we will be discussing more 2 weeks from now. But already a small introduction, see how if your logic skills still hold up. See if you can figure out whether this thing is true or false. All right, 10 seconds left to give me an answer if you have one. And let's take a look. So, what do you think? 4/5, 80% for answer A. Excellent. Yes, this thing can indeed be made true. I was gonna ask for someone to give me an answer, but I see some people have already been posting them in chat. Great. So yes, if you take a look at the first part, right, x0 and x1 and x2, this part we cannot make true for all x1, which is one of the requirements, because x1 is false, is also an option for x1, and so the first part cannot be made true. The second part, however, we can make true by simply making x4 true. And since for x4 we only need to pick one value, pick whatever else you like for the other ones, so long as you make x4 true, this whole thing is true. So indeed, we can make it true. Just take x4 equals true. All right. Let's see if there was something else I wanted to do here. No. So like I said, the encoding problems, a topic we don't talk about all that much in this course, because although it's very nice to see that we can encode different problems in such a way that a Turing machine can reason about them, it's something we hardly ever need to do. There are some more practice questions for you available when we post these slides on Brightspace, but it's not the main focus of this course. What is quite a bit more important, though, is the topic of decidability. And we are about to get that started. Let me take a look at the time. Yeah, we can do one question before the break. But before we do, let me quickly see if there's anything new here. I thought I already answered this, but apparently I clicked the wrong button. Is a language Turing recognizable if and only if there exists an enumerator that enumerates it in alphabetical order? Or is the order only important if we want to conclude a language is Turing decidable? Very nice question. Very nice question. Let me make it actually a bit bigger here. This can probably help. So is it recognizable if and only if there exists an enumerator, or is the order only important when we want to conclude it's Turing decidable? So a language is Turing recognizable if and only if there is an enumerator. And for that enumerator, the order does not matter. Any order will do. If we want to indeed conclude that it is decidable, what we have seen is that then an ordering is important. So we have indeed seen that if the enumerator that exists for it is in alphabetical order, then the language must be decidable instead of recognizable. So that's quite a bit stronger, if you will. I hope that answers this question. I see one more question has popped up. What does TQBF have to do with this course? Well, nothing yet when it comes to our discussion of computability and decidability, but we'll see it pop up again when we talk about the complexity theory part of this course, and that's why I decided to keep it in. Okay, let's do one question about decidability before the break, and then let's have another 15-minute break. So, decidable languages, our last topic of today. Let's get started with what is hopefully a quite doable question, but we'll find out. There's a D of A here, and my question is the tuple D1 AAA, is that in the language A D of A? I'll give you, let's say, a minute to answer that question. Okay, a couple of seconds left to give me an answer if you have one. Minute may indeed have been overkill, but we still seem to be able to reach 50 people. Ah, very nice. Almost 100% for answer A. So is it in AD of A? Well, remember, AD of A is the set of machine word tuples such that the machine accepts the word. And indeed, this machine accepts the word AAA. We start at Q0, we go to Q2, we stay in Q2, and we stay in Q2, which is an accepting state. So indeed, this tuple D1 AAA is in AD of A. One last question I can answer before I send you off into a break, which is the question I was just asked. So what do these angular brackets represent, right? Why are they there? We use them to denote, let's say, a string version of the input. So our decider or our Turing machine that would decide or recognize AD of A cannot take as its input another machine, right? We need to encode it in some way. And to indicate that we're talking about the encoding, we use these triangular brackets. Does the order of the input matter? I guess you could define AD of A also for tuples in a different order, but I've only seen definitions that take the machine first and the word second. Okay. I see no other questions at the moment, so let's have another break. I think it's about time for that. Yeah, it's 3:30. So let's have another 15-minute break, and once we get back, we'll do some more practice with decidable languages, and I shall try and make the questions a little bit harder so that not 100% of you get it right. See you in a bit. All right, so let's try to get this started again. I realized I forgot to say this earlier, but thank you all for sticking around. I realize this is not the most ideal way of following lectures, perhaps, but I think we're sort of making do. I hope you agree. Let's take a look at this topic of decidability that we still have left. So just before the break, we took a look at this first pairing of a DFA and a word, and we concluded that yes, it must be an ADFA, because indeed this machine accepts this word. Well, let's knock out one more relatively doable question, or at least I hope so. So here is the second one. Let me also open it up in feedback fruits. Same machine, different word machine pair. And I'll give you, well, however long you need to put your answers into feedback fruits, but hopefully we can do it in half a minute. Let's find out. Okay, 5 seconds left to give me an answer if you have one. And let's take a look. So, ooh, very nice, almost 50-50 split. Yeah, so I was trying to trick you a little bit here. We talked a little bit about ordering before the break, right? Does it always have to be machine followed by word? Well, in our definition of ADFA, yeah, it has to be. So for our definition of ADFA, this is indeed incorrect, because our definition requires a description of a machine or of a DFA before the description of the word, whereas this description starts with the word and then gives the DFA. So indeed, as Jonathan points out, they're in the wrong order here. The other way around, so D1, BBA would be in ADFA, because if we take a look, B goes from Q0 to Q1, another B to go to Q2, and then an A to stay in Q2. So BBA, so D1, BBA would be in the machine, or would be in the language. I'm messing up my words here. D1, BBA would be in the language, but this way it doesn't, or it's not, because BBA needs to be a machine, and this is a word. The order is wrong. And indeed, as Hyper points out, Paul, we're just putting strings into a Turing machine. So there's no way of type checking it, let's say. We could, of course, start a Turing machine that decides ADFA by saying first check whether the input starts with a valid description of a Turing machine. Jonathan, will we ask questions like this on an exam? Well, I don't think this is really an interesting question to ask on an exam. Technically speaking, that's not a no, but I hope you can do something with that regardless. All right, let's move on to the next one. So here's another machine. Let's call it D2. Now I wonder whether the tuple D2, D2 is in EQ DFA. Feedback Fruits is happy to hear your answer. And let's see what you think. Okay, currently at 40 people. Let's see if we can reach 50 again. A couple more seconds. It's also started raining outside. I hope the mic doesn't pick up too much of that. And let's take a look. Okay, so about 80% of you got this question right. So indeed, D2 is in EQDFA. Now, what does EQDFA ask? So EQDFA is the set of all. I should make my webcam a bit smaller maybe so that we can fully read this. Something like this. It's the set of all. It's the language that has all of the tuples in it of two machines such that the languages of these machines are the same. So the language of M1 is equal to the language of M2. Now, D2's language is, I would almost say, trivially equal to the language of D2. So indeed, D2 is in EQDFA. I see no questions about it. So let's move on to the next one. Now we take D2 and we take a machine called D3, and I wonder, is this tuple D2D3 in EQDFA? Or sorry, rather the description of the tuple D2D3, is it in EQDFA? Again, I'll give you a bit of time to take a look and to give me an answer in feedback fruits. Sorry, it seems indeed that feedback fruits was hiding one of the transitions. I've made feedback fruits a little bit smaller so that you can see the transition. Okay, we are over 50, so that's good enough for me. Let's take a look. 100% for answer B. All right, very nice. Very well done. Answer B is indeed the right answer. Now, I believe when I click here, I also show a counterexample, but perhaps one person could already give me one in chat. That also gives me some idea of how bad the delay actually is. AAA is given as a counterexample. Let's check that one. Okay, so AAA is indeed in D2, right? We just follow all the transitions. But if we take a look at the other one, AAA, we indeed go from Q0 to Q1, we go to Q2, and we stay in Q2, meaning it's not accepted in D3. So that's a good counterexample. There's a couple of more answers given. Epsilon is the one I had in mind, but it turns out it's not on my slide at all. But yeah, epsilon is not in D2, but it is in D3. So indeed, these two machines do not have the same language and therefore are not equivalent. Okay. Hyper, remember that DFAs can perfectly accept empty strings. We're just not allowed to have empty string transitions. But there are definitely languages that contain empty strings that a DFA can accept. People seem to be claiming that the machines are opposites of each other, so they are each other's complement. I haven't checked that, but you might very well be right. Well, the string A is in neither, right? So they are not exactly complements, but it could very well be true that they share not a single element. That is, yes, because for D3 we always need a B in there somewhere to still be accepted. So yeah, I think you're quite right. They don't share a single element. They are indeed distinct, the languages. Can they be complements if they have different alphabets? Well, it would be tricky, but for example, both could have the alphabet AB. One could accept A star, and the other could accept everything except A star. And then I think it's perfectly possible. Well, okay, so depending on what you think of as the alphabet for the one that accepts A star, right? We can say the alphabet contains both A and B. All right. Let's move on to the next question. So now we have 3 machines. And my question is ABBA an element of ADFA? This should hopefully be really quick. Okay, a couple more seconds to give me an answer if you have one. And let's take a look. Okay, perhaps slightly trickier than I expected. Quirky is absolutely right in the answer that they just gave, however. Remember, ADFA wants a machine word pair, right? It is the question, does this machine accept this word? Or does this DFA accept this word? So it wants a DFA word pair. So just the word ABBA is never going to be in ADFA. ADFA needs one of these pairs. And just a word is never going to be in there. So the correct answer is indeed no. We could take a look. So for example, ABBA, no. Only, yeah, so only the pair D1, ABBA, or the description of that rather, would be in ADFA, because only D1 accepts the word ABBA. Both D2 and D3 reject it. Okay, let's see if we can get to a somewhat more interesting question now. Yes, okay. This one is rather nice to see if you know what eDFA is all about. So the question asks, which of these 3 DFAs is in eDFA? And Feedback Fruits is happy to hear your answer. Okay, a couple more seconds to answer this question if you have an answer for me. Okay, let's take a look. Answer D is by far the most popular. So yeah, someone already asked, right? What is this EDFA that we're talking about here? So EDFA is the set of all DFAs which recognize the empty language. Note that the empty language is also a language. So arcade, unfortunately, your answer isn't quite right. Right, so a language that has no words in it. Sorry, lost my train of thought there for a second. So a language that has no words in it, if the DFA has, or the language of the DFA is the empty language, then it is in EDFA. Now for D1, D2, and D3, we can quickly come up with counterexamples. So for D1, take the word A is in the language, so therefore this is not in EDFA. For D2, take A, that's in the language, so D2 is not the empty language. Or D2's language is not the empty language. And D3, take epsilon. Epsilon is a word, it is the empty word, and therefore D3 is, the machine of D3 is, its language is not empty, and therefore it's not in EDFA. Now you may ask, okay, but then give me a DFA that is in EDFA. Well, I can give you a trivial one. Take one that has no accepting states. So a DFA without any accepting states has an empty language and is therefore in EDFA. Alternatively, we could think of some sort of disconnected graph, so there is no path from the start state to an accepting state. If you have no states at all, it's a bit tricky to see whether that's an automaton or not, because we always need a start state. So without any states at all, I would argue that that's not an automaton. Right? If you remember our tuple definition, it's sigma, q, delta. Now these could all be empty theoretically in our definition, but then we need a q0 that is a part of q. And if with an empty set of states, we cannot have such a q0. So our tuple definition wouldn't work for machines without any states. Okay. Let's move on to the next one. So now let's talk instead about context-free grammars for a bit. So we have a context-free grammar G, and we construct it in such a way that the language of this G is equal to the language of our machine D here. Now then, which of these claims must be true? I'll give you a minute or so to read them and to give me an answer. All right, one issue with using your phone as a webcam is that you can get a phone call. I indeed forgot to open the question. Sorry for that. I've opened it now. Fortunately, you're very quick in filling it out. So a couple more seconds to give me an answer if you have one. Then we'll take a look. Okay, let's figure this out. So let's take a look at your answers first. Ooh, very overwhelming majority for answer C. So how about we start with that one? What does it say? D1, BBBB, 4 B's in total, is a member of ADFA, or is an element of ADFA. Let's take a look. When we start in Q0, we take B to Q1, we go to Q2, back to Q1, and back to Q2. So indeed, answer C is correct. Some votes for answer B, so let's very briefly discuss that. Answer B says G, D1 is an element of EQ-CFG. Well, remember, their languages are indeed the same, right? That's how we constructed our context-free grammar. However, our EQ-CFG requires two grammars to compare. And D1 is not a grammar, it's a deterministic finite state automaton. So that doesn't work. There's a nice question by Paul here. G must be a regular language if LD1 is LG, right? Well, as Hyper points out, G is a grammar, so therefore not a language. But I see what you mean. Indeed, we would have a context-free grammar representing a regular language. But that is definitely possible. Someone else with a nice Dutch username, Ik ben altijd wakker, is asking us, what does the notation in D even mean? Answer is, I don't know either. The notation makes no sense to me, and therefore clearly it's a false answer. Quirky, you're asking, okay, but this EQ, isn't it only defined for DFAs and not for grammars? Well, we have two different variants. So one you see in answer B and one you see in answer E. So we have EQ DFA, which we discussed before, which is for deterministic state machines. And we have EQ CFGs, which is for context-free grammars. So both of these problems exist. Yeah, both of these exist. One looking at the equivalence of deterministic finite state automatons and one looking at the equivalence of context-free grammars. Okay. I see no other questions, so let's move on. Shall we do this one? No, let's skip this one. Let's take a look at this one instead. I think it's slightly more interesting. So we have a new machine D4, and the question is, this machine D4, is it in eDFA? Feedback fruits should be happy to hear your input. All right, let's give you 5 more seconds. Apparently screen delay is okay. So a couple more seconds and then we'll take a look. We've reached 50 people again. which seems to be roughly where we strand every time. Let's see. Answer B, by far the most popular. Indeed, this is not in EDFA. Why not? Well, the answer was indeed already spoiled a bit in chat, but yes, you did give the correct answer, Frostbite. It accepts the empty string, and therefore it does not, or its language is not empty. So these are really two distinctions, right? We have an empty language, that means there's no words in it at all, and we have the empty string, which is a word. So if that word is in the language is not empty. Klaas Vaak's asking, is there also something like this, this EQ that we just discussed, right? EQ CFG, we saw EQ DFA. Is there also one for Turing machines? Yes, there is. Problem is that one is even trickier, but we'll discuss it a little bit next week. Jonai, is there a way to know about what all of these things mean? EDFA, EQDFA, EQCFG, etc. Yes, read the books, do the homework to prepare for these sessions. I'm sorry if my answer is a bit of a nasty answer, but we do discuss them there. Hyper, remember that EQTM is simply a problem, right? It doesn't mean that the problem also has a solution. Just like how the halting problem is also a problem, doesn't mean that it also is, and doesn't mean it has a solution. So EQTM definitely exists, but we don't know, or we know that there is no solution for it. But like I said, we'll discuss that more later. All right. I think that's all the questions. Yeah, and Jonah, indeed, you need to know these by heart. So on the exam, I expect you to know what EDFA means, what EQCFG means, stuff like that. Okay, next up. Now, we have a grammar, and instead of ADFA, we're going to take a look at ACFG. So here's some grammar with some rules. Is the description G, AABBA in this language? The question is open in feedback fruits. Okay, a couple more seconds to give me an answer if you have one. All right, let's take a look. Now, someone asked earlier today on Brightspace, I think, do we still need to know the material of the midterm for the end term? And my answer was, well, no, technically speaking, the end term is about different material, but questions like the one we are currently facing requires you to know something about the midterm material, right? So we wouldn't ask you to rewrite something to Chomsky normal form on the end term. We wouldn't ask you to do a proof with the pumping lemma. But we do expect you to still know how DFAs, NFAs, CFGs, how these things work. And of course, especially Turing machines, because we'll be talking about them a lot more, to answer questions like this, which are about languages that, as their element, have context-free grammars or Turing machines or DFAs. So no longer the, let's say, constructive work of transforming one into another, but still definitely how they work. Now let's take a look at this question. Overwhelming majority for answer B. No, it's not in there. I agree. If we take a look at this language, all it accepts is A star, B star, as someone also correctly pointed out in chat. Quirky was the one to do so. Yeah, because indeed all we can do is we can have a number of A's by transforming our S into an A to start with. We can have a number of B's, transforming our S into a B to start with, or we can have a number of A's followed by a number of B's. But this, let's say, alteration of going from A to B and then back to A, that's not possible here. All right, someone was curious earlier, are we gonna be able to do all of this in the 3-hour lecture slot that we have? The answer is yes, because I have only one last question remaining. So let's take a look at that one. If you have any more questions in the meantime that I can answer at the end, feel free to ask them already. But also please take a moment to think about this one. So we have a push-down automaton here. It's a relatively simple one with only one state. My question is it in ECFG? All right, we've reached the magic 50 again. So let's take a look. Ooh, okay, managed to trip you up with the last question after all. Very nice. 2/3 go for yes, 1/3 goes for no. And I see that just at the end here, Autobot added the wrong thing as spam. Yes, so Quirky is right here. P1, and also Hyper now, P1 is a PDA, it's not a grammar. And remember, ECFG only contains grammars whose language is empty. But P1 isn't a grammar, it's a PDA. Now this P1 would be in ePDA, right? Because the language of P1 is indeed empty. But it's not in ECFG because CFG only accepts grammars that have an empty language. All right. Yeah, a bit of a trick question, Pineapple, but I think it's nice to end with some tricks every now and again. So let's see. And before I do that on stream, let me do that here. Yes, okay, that seems to be fine to open. So 2 questions that were posted through Feedback Fruits. If you failed the midterm, are you doomed to the resit? Quite strong wording there. Or does your grade for the end term in that case still influence on your final grade? No, so this course has a minimum requirement of a 5 for the midterm and the end term, and only a resit for the combination. So indeed, unfortunately, if you have lower than a 5 for the midterm, you will have to do the resit for the course. The other question asked in Feedback Fruits was, are 2 Turing machines equivalent, EQTM, if they accept the same words, but the one rejects for words while the other one loops? So we will talk about this a little bit more next week when we talk about EQTM. So how about, if you don't mind, I set that as a little bit of homework for you. Try to figure this one out yourself first, and next week we can discuss it here. Good, then let me hide feedback fruits. We have 5 minutes or so left. Let's see if I can answer one or two questions that chat is putting up. When will you get the scores for the midterm? Well, as you can imagine, hopefully Moogle, things have gone a little bit differently than anticipated over the last few days. Matthijs was originally planned to give this lecture. I only decided to take over last night when we heard that on-campus education would really no longer be an option. So today, instead of spending it grading, I spent preparing for this. It's also a bit trickier now to get TAs together to arrange some stuff for grading. So we're working on it, but at this moment I have no time frame for you. How do I like this way of lecturing? Well, so far so good. Personally, I don't see this as a good replacement for regular lectures. I find it a bit odd sitting here in a room talking to myself. But, well, I think we're making do so far. Let's see. Paul, on the exam they asked us to use the book's method of converting to CNF. Do we lose all points if we did so in a slightly different fashion? Well, it depends on what's slightly different in this case, I guess. But yeah, without looking at your answer, I find it very hard to say this. My gut feeling would be no. You can probably still get at least a part of the points if you use a different way. Anything else? Okay, yeah, one last question here just at the end. What's the recommended way of going from a PDA to a CFG other than the method of Sipser? Well, when in doubt, I would say always use the method of Sipser. So this is true for any of the transformations we've seen in the course. Anything that we can do using the method of Sipser is great because it's a method that always works, right? No matter what the input looks like, we have a set of steps we can do and we get to our output format that we want. So for example, an NFA to a DFA, we can always do using the method from Sipser. That being said, sometimes it might be nicer nicer is not a great way of saying it, but it might be more efficient maybe to analyze, okay, what's actually the language of this machine or of this grammar or of whatever we have or of this PDA, and how can I create something in a different format that has the same language. That's a much more creative exercise, which is great, but yeah, it requires a whole bunch of creativity, and as a result there is not really a structured approach. It really relies on looking at the languages and trying to find a different representation for that same language. Okay. Paul, I see. I don't think that will be too much of an issue. But again, I can only really take a look at this when I take a look at your answer. So no guarantees yet. Hyper, you are absolutely right with your statement there. So indeed, a 4 between these angular brackets and 2 plus 2 between angular brackets are two different inputs to a Turing machine, right? They're two different strings. That's a good way to think about them, and therefore they are different for our Turing machine. All right, I think that's going to do it for today. So looking ahead a bit, we have another one of these interactive sessions scheduled for next week. I expect we will be using a somewhat similar setup, but I'll be keeping you informed next week and let you know how we proceed. For the last 2 lectures of this course, which were meant to be, let's say, more classical lectures in which I talk about complexity theory with you, we still need to see what's going to happen. I have requested College Gamma for those, so that next year we can have the same flipped classroom style as we have with the other content. So that means I might go to Lecture Hall Ampere stand in an empty room there and do the lecture there, so that at least we have the College Rama material. But I'm still need to see whether that's going to work or not. I can also imagine that I'm going to find it even more awkward to talk to an empty lecture hall than I already find it talking to my phone and you guys digitally here. So we'll need to see, basically. No guarantees yet. Okay, I think that's it. So I'm going to cut it for now. Thanks for being here with me. Thanks especially for the last half for really making this work. And see you around soon. Enjoy your weekends.